Alright guys, so as I described in the assignment today, here's what I would like for you to do. I would like for you to read each question or listen to me read it, because I have a lovely reading voice, or just mute me, that's fine. So read the question, pause the video, write down what you feel is the correct answer. Please write down something. All right. As soon as that's done, you can go ahead and play the video again, and I'll talk you through the correct answer. Once you hear the correct answer, please pause it again before it goes on to the next question. Go ahead and annotate your answer in a different colored pen or pencil. This way you know and I know what you've gone through and you've changed to fix your answer so it's better than it originally was. All right. I want you to do that for all 11 of these questions. Okay. If you do that, that's the only assignment for today. But I do want you to be committing to an answer, thinking about it, fixing the answer, and making sure that everything's all right. Okay? So here we go. Question number 1. A mass is oscillating back and forth on a spring without friction as shown. At which position is the magnitude of the acceleration of the mass a maximum? Position O is the relaxed, unstretched position of the mass. All right, go ahead and pause it and put down your answer. All right, here we go. So let's talk about it. So it says that position O is the unrelaxed, unstretched position of the mass. So that means that O is our equilibrium point. Okay, because that's unstretched. Remember, as soon as I take my block from O and I stretch it in this direction, the spring here is going to be pulling back in the opposite direction, right? We know that it's always pushing back towards equilibrium, back towards the center. So any place I am to the right, the spring is going to be pulling to the left. As soon as I pass this 0 and I come over to the left-hand side, then it's going to be pushing it right back towards the middle. Any position over here means that the spring has been compressed and it's going to be pushing over to the right. All right, so that's an important idea when we come to answer the question, which is, at which position is the magnitude of the acceleration a maximum? Well, remember that force equals mass times acceleration, right? So it should make sense if the mass isn't changing. When the force is at a maximum, then the acceleration should be at a maximum. All right, so when is the force going to be at a maximum? We know that as well, force equals kx for a spring, or negative kx because it's in the opposite direction. So since k is a constant for a spring, the force is going to be a maximum when the displacement is a maximum. Okay, so the displacement from 0, when is that a maximum? Well, it's a maximum at E. That's the largest distance you're away, and you know this about springs. The larger you pull it away, the harder it's going to pull back the opposite direction. The harder it pulls back the opposite direction, the greater the acceleration. Therefore, the answer should be point E. Hopefully that's what you got. Moving on. Again, same situation. A mass is oscillating back and forth on a spring without friction as shown. At what point is the total energy of the system at a maximum? Position O is the relaxed, unstretched position of the mass. All right? Go ahead and pause the video. All right, well, this is somewhat of a trick question. Not a trick question, it's just making sure that you understand the idea behind the question, right? When it's at 0, when the block is at 0, it's not stretched, which means that there is no energy in the spring, okay? But what that means is that when it's at this position, it's got to be moving, right? That's what happens. It gets pulled out to E. As it gets pulled out to E, you release it, and what happens? It flies back in the other direction, right? It gets pulled back this direction until you get to 0, after which when you pass by, it starts pulling it back in the other direction and slowing it down. More pushing it, I guess. It's pushing it back in the opposite direction, okay? So what that means is that I have high potential energy on the ends, elastic potential energy, because the spring is either compressed, ready to push it back out, or it's stretched, ready to pull it back in. And then in the middle, I have high kinetic energy because all that potential has been turned into kinetic. Now, ideally, and we're going to consider an ideal situation here, What does that mean? Well, ideally that means that when is the total energy a maximum? Well, the total energy is never a maximum or always a maximum because energy is conserved. Because it's without friction, no energy is being lost. Therefore, energy throughout the system is being conserved. No extra work is being done. The energy of the spring is taken care of in our elastic potential energy here. So therefore, it's always a constant. Next question. The position of a mass on a spring as a function of time is shown below. Note that this shows the specific. Yeah, I can spell specific. You knew what it meant even if I didn't write it. Tell your English teacher it doesn't matter how you spell it as long as you get your point across. Shows the specific position of a specific point on the spring. At the time corresponding to point P, determine individually whether velocity and acceleration are positive or negative. All right? So we do have time passing on. Okay? And then the y-axis, it says, is the position on a spring. Okay? So we have to assume that this right here is our equilibrium. Right? Okay, this x, it doesn't say whether it's going vertically or horizontally, so it doesn't really matter. We're just going to consider that's positive position, this is negative position. So let's look at the p. Let's look at the p. As time progresses, as time moves on, okay, what is going to happen to the mass, right? Well, it started here, it went far away from equilibrium, came back, far away, right? And so this is what the mass is doing. So if this is where it is right now, where is it gonna be in the next instant? Well, it's moving that direction time, and so that means that it's going to be moving upwards, okay? Now, what does that mean about the velocity? It means I have a positive velocity because my displacement is becoming more positive. Okay, now the acceleration is a little bit more tricky question, but you have to remember that if my displacement is positive, then the force has to be negative, right? This is where we get that F equals negative kx. It should also make sense that anytime you have a spring, if this is the equilibrium point, and if I stretch it, and I have a positive displacement, then the force is going back in the opposite direction, which means the force, if the displacement is positive, force has to be negative. Same thing the other direction. If I push it in and my displacement is negative, the force has to be pushing it back to equilibrium. So therefore, if I have a positive displacement, the acceleration must be in the opposite direction, or negative. All right? Next up, the solid curve below is the original wave. What is the sign of the phase change of the dotted graph? Can you estimate a value for the phase difference? Go ahead and pause it. All right, hopefully you've had a chance to work through it. It does say what is the sign of the phase change? Well, everything that says the solid curve is the original and then the dashed is the new one. So the phase change is that the positive, the maximum, has moved over that far, right? So it's moved over that much. Any point on the graph you could look at, it's moved over that much. Okay, so the first thing is it's moved to the right. So therefore, the sign of the phase change is positive. All right, and we're good with that. Okay, can you estimate a value for the phase difference? Well, that may be a little bit more difficult, but if I look at the phase difference right here, okay, that distance, if I repeat that, it looks like it's about a quarter of one hump, right? Oh, no, actually it's about let's see. So I go from the top, it takes me 3 to there, 1, 2, 3 to the bottom, 3 to get me over here, and then 3 to get back to the top. So it looks like I need 12 spaces and the shift is one of those 12. Okay. If you guessed 1 out of 8, that's probably all right as well. Okay, as long as it's somewhere in that region of, it's less than a quarter, right? This would be a quarter right there. So it's got to be less than a quarter for sure. Okay, next one. An object hangs motionless from a spring. If the object is now pulled down and held, does the sum of the potential energy of the spring and the gravitational potential energy of the object increase, decrease, or stay the same? Pause the video. All right, here we go. So I've got an object hanging at the end of a spring, just like this. And then we go and we pull it down. So the question is, does the sum of the potential energy and the gravitational potential energy increase, decrease, or stay the same? Okay, now some would say, well, it's going to stay the same because the elastic potential energy is going to increase because I'm going to stretch that spring downwards, but the gravitational potential energy is going down, so they balance each other out. Well, I hate to break it to you, but that doesn't actually work. Because if you say that, then that means that no work was done on the block, that no energy was added in, but energy was added in. I had to grab that with my hand, and that's my hand. See, there's my lovely fingers and my thumb. So I am grabbing it. I have to grab it and pull it downwards to stretch out that spring. Now what that means is that the energy now has to be greater than the original energy, right? Because I had to do work. I had to take this block and move it down. And so since I had to do work in order to accomplish that, then there must be more energy now because I added energy in. All right, so does the gravitational potential energy go down? Absolutely. Does the elastic potential energy go up? Absolutely. But the elastic potential energy must increase more than the gravitational goes down because the total energy must go up because I put energy into it. All right, fun. Doing well. Cruising along. A stiff spring and a floppy spring have potential energy graphs as shown below. Assuming that both springs have the same scale, which is the stiff spring? Go ahead and pause the video. You ready? I'm ready. Let's go on. So remember that the elastic potential energy of a spring is equal to 1/2 kx squared. Okay? Now, note that in both of these graphs, assuming they have the same scale, in both of these graphs, they both get to the same elastic potential energy. Okay? Now, in order for that to happen, this one right here has a much smaller x, right? If it has a much smaller x, what has to be true about k in order to get the same elastic potential energy as the one with the bigger x? Well, the k here must be bigger. And a bigger k means a stiffer spring. Now, that, my friends, should make sense logically, right? Should make sense because if it is a stiffer spring, I have to pull harder on it in order for me to be able to stretch it, right? The same amount of energy with a stiff spring is going to get a much smaller effect if it's stiff as compared to if it's not very stiff, if it's loose. Then the same amount of energy, the same amount of work that I do will be able to stretch it out much, much more if it's loose, which would be this situation right here. So think about it conceptually, think about it with the equation, right? Keep elastic potential energy the same because of that. The distance is shorter here, displacement is shorter. Because displacement is shorter, k must be significantly larger. All right, next question. Change gears a little bit here. Which of the following is least likely to occur? Transverse waves in a fluid, longitudinal waves in a fluid, transverse waves in a solid, longitudinal waves in a solid. Go ahead and pause the video. And here we go. So which is least likely to occur? Well, remember transverse means that the particle is moving up and down, and yet the wave is moving to the right. Okay? A longitudinal wave, I'm going to write it out, is where the particle is moving to the right and to the left, and the wave is moving to the right. Right? So when we talk about the wave, we're talking about the energy. Okay? Now, longitudinal makes sense because as I move this way, if I bump into another particle, then it's going to move that way, and if it bumps into another particle, it moves that way. So longitudinal can pretty much happen in any type of material, right? That's not a big issue, okay, because the particles are just going to vibrate back and forth. As they do, they're going to bump other molecules, and the energy is going to be transferred down the line. So longitudinal can happen in a fluid. It can also happen in a solid. A fluid is a liquid or gas. Okay, anything that'll take the shape of its container, whether it fills it or not is not the question. If it will fill the container, if it'll change its volume, not its volume, but its shape in order to fit the container, that's more or less a fluid. All right, so we've said that longitudinal can happen either way. Transverse is where it's moving up and down. You know, a great example of transverse is like a string, right? If I'm standing here holding a string, and you are standing over there because you miss me and you want to do some physics with me, so you're standing over there. If I start to move my hand up and down, what happens, right? A wave starts to occur in the string, and a wave is going to move. As long as I keep moving, this is going to move down this way. Now, recognize that my motion is up and down. The motion of the energy is then this direction, perpendicular. So transverse, the motion of the particles and the motion of the energy are perpendicular. In longitudinal, the motion of the particle and the motion of the wave are parallel. Now, in a solid, this works, right? Like with a string or a slinky. Hopefully when you guys come back from break, we'll be able to do a lab with a slinky. This is one of my favorite labs, is just kind of playing around with waves a little bit and figuring some things out. So it works really well in a solid, that's fine. But a fluid, think about those particles, right? If I've got my particles in a gas or a liquid or something like that, if this particle starts moving up and down, is it going to affect the particles to the side of it? The answer is no, right? It can't affect those particles. The energy is not going to move in this direction in a fluid, right? The only exception would be if you have some type of fluid that has some type of adhesive properties like hydrogen bonding in water or something like that. You may be able to get a little bit of transverse waves, but that is the exception. That's not the rule. Generally speaking, in a fluid, the particles are not interacting with each other a whole lot, and so therefore this is not going to work. So the answer is letter A. All right? Which of the following waves could be considered completely or partially transverse waves? Okay, so pause the video and go. The wave made by fans at a sporting event. Okay, well, which direction? Remember transverse. Transverse means that the particles are moving up and down, and the wave is moving perpendicular. So that's what we're looking for. All right, the wave made by fans at a sporting event. What direction do the fans move? The fans stand up and they sit down, but the energy of the wave moves to the right. So that, my friends, is more or less a transverse wave. All right, waves on the surface of a lake. Waves on the surface of a lake. Well, waves on the surface of a lake, hopefully you read about it, are a little bit weird because they have a couple of things going on. They're actually moving kind of in circles, But the important thing is that part of that circle requires some up and down motion. And we know that the wave is moving to the right perpendicular to that. So we'll say that at least partially waves on the surface of a lake. Granted. Next up, sound waves in the auditorium. Well, remember, sound waves are through air, right? Air is a fluid. Fluid is a gas or a liquid. So if that's a fluid, it is very unlikely that it's a transverse wave. And in fact, we already know that the way that sound works is that these particles move, they bump into other particles, which then bump into other particles. That means that the movement of the particles and the movement of the wave is parallel. I don't even need to look at the last answer because sound waves in the auditorium will not be transverse waves. TV signals, well, those are electromagnetic waves, which actually have two sets of transverse waves. One which is the electric wave, and then one which is perpendicular to it, which would be kind of coming out of the page here. Okay, that's the magnetic wave, and those will be perpendicular to each other. But yes, it will be at least completely or partially transverse. The only one that's not in any way, shape, or form is this sound wave. All right? Next question. The image below shows a snapshot of a wave traveling on a string. Note that the velocity of the wave is to the right. Point P has a spot of paint. At this instant, the paint spot has a velocity in which direction? Okay, so notice this is a little different from the other question that we had. Pause the video. Man, I was just way too excited about this question. Just ready to move along. So, recognize this is a little bit different, right? It shows a snapshot of a wave traveling on a string. Okay, so this is the actual string here, right? At a specific point in time, here is my string. Parts of the string are up, parts of the string are down, right? But this is the position along the string. That's X. And then Y is how far it's been displaced from its center, right? Which is this. So it really is just basically what you have there, okay? Recognizing that in just a split second, the wave is going to move to the right, right? Because the wave is moving to the right. So in just a minute, this guy is going to be moved over like this. Okay, now this is an important part of the problem-solving process, is recognize where is the wave going to be in a minute. Okay, now recognizing that the string isn't actually moving, right? I'm shaking it up and down, okay, which means that the whole wave is moving up and down, but in reality the string is staying where it is. Okay, now what's going to happen to this point P? Okay, well, what type of wave is this? This is a transverse, right? We talked about shaking the string up and down before, shaking it up and down, and what do we get? Well, we get a little bit of standing wave there if you do it at the right speed. Okay, so it's a transverse wave, which means if the wave is traveling this direction, the particles must be moving up and down. And by drawing what the wave would look like in just an instant, knowing that it's moving to the right, we can actually see that P here is going to move down. It's going to have downward velocity. That's kind of weird. It's kind of different, but it's also really, really neat what we can do with that. All right, so there you go. Point P is moving downward. All right, next up, we've got a string clamped at both ends. You can see I've got a standing wave here, so this is fixed here, fixed here. It's got some type of vibration or something so that it is moving back and forth. You've got equilibrium here, you've got where it goes up here, and then it is a standing wave, so it goes back down there. Okay, let upward motion correspond to positive velocities. When the string is in position B, instantaneous velocity of points along the string is 0 everywhere, positive negative everywhere, depends on the position. Go ahead and pause. And here we go, yes we go. Oh, here we go. So we need to figure out what these different things are doing as it passes through this line right here. Okay? Well, I can already tell you that some of these positions, well, why don't you tell me? What's happening at these positions? Is the string actually moving there? No. The velocity of those points is 0 because those are nodes, right? At the node, the string is moving up and down around it, but that point in space actually is not changing. Okay, so we actually have 0 velocity at the node. Now, this guy, when he gets to the middle here, right, he's going to be moving downwards. He's not stopping there. He's not at 0. So the velocity anywhere else is not 0. Okay, which means it's not 0 everywhere. It's not positive everywhere because some places it's 0. It's obviously not negative everywhere. So therefore it must depend on the position, right? If my string is below, then as the string gets to B, it's moving upwards, right? So it would have a positive velocity. This part, as it moves down to the middle, when it does reach there, will have a negative velocity because it's going downward. All right, so it's a good combination of ideas there, looking at what direction will this string be moving. Last question. Here we go. Yeah! A trombone is played in a room filled with helium. The speed of sound is 2 times that in normal air. So how would it affect the pitch of the trombone? Would it sound the same? Would it be higher? Would it be lower? Or would it be unpredictable? Justify your answer with both anecdotal evidence and also using a formula or two. Pause the video. And here we go. All right, so let's talk about anecdotal evidence first. Have you ever seen somebody, or have you ever been the person that sucked the helium out of the balloon? What happened? Your voice got really high, didn't it? So we already know the pitch would be higher than in normal air. All right, so let's see if we can make sense of that with a formula or two. Okay, so what happens if the speed is faster, right? The speed is faster. Now, what's happening, and I'm gonna draw a simple trombone here, right? Is that inside the trombone, we're getting a standing wave, something like this, all right? The shape of that wave isn't going to change really too much, okay? So we have to have an antinode at the open ends. Really, that has to happen. You have to have the antinode there, okay? So what would happen if the wave was twice as fast, okay? Assuming that the wavelength couldn't change, okay? Do we have an equation that relates the speed of the wave and wavelength? Well, hopefully you either read in your book or you remember from past classes that the speed of the wave is equal to the frequency times the wavelength. Well, if the wavelength doesn't change because it's stuck in these positions in order to make a sound, to have these, we'll talk more about those fundamental frequencies later. If that's not changing and the velocity is double of what it used to be, what has to change? It's got to be the frequency. The frequency also has to double. Therefore, higher frequency means higher pitch. All right? Great job, guys. That's all 11 of them. I want you to go take a break, or if you haven't finished something, why don't you go work on that? All right? And I'll give you some more stuff coming next week. All right? Thanks a bunch.